Hello everyone, my name is Sheng Di. I'm from Argonne National Laboratory, and in this talk, I will present a new lossy compressor that can preserve quantity of interest for scientific data sets. In this talk, I will first introduce the background and then related work, and then framework design as well as the problem formulation. Because of the limited time, I will skip the detailed proof and then I will show the evaluation results. As you know, today's scientific simulations are producing very large amounts of the data. For example, climate simulations can generate over 200 terabytes of the data within 16 seconds, and the fusion simulations may produce over 200 petabytes of the data in a single run. So how to deal with such a large amount of the data is very challenging, especially for today's database and data management. The many users are using cheaper and faster storage or larger scale computer clusters or heterogeneous computing architectures to resolve such a large amount of data. But all of these solutions are may face some significant issues, especially when the data size grows very large. For example, the storage always has a limited capacity, and the I/O bottleneck may also keep growing over time because of the significant gap between the I/O performance and the computational power. So many users are trying to leverage the lossy compression to significantly reduce the data size, for example, using ZIP, SD3, and mGuard. However, lossy compression may introduce the data distortion on those data sets, so this may result in significant concerns on the reconstructed data. As you know, many users are very concerned about the post hoc analysis. So there have been quite a few existing lossy compressors supporting preserving the quantity of interest during the compression, but unfortunately, none of them can cover all of the quantity of interest during the compression. As shown in this table, for example, a Z can preserve L infinity, L2 norms, and the point-wide relative error bounds, but it cannot support the linear QI, quadratic QI, and topological QI. And our solution will fill this gap. These slides demonstrate the related work in the compression community. There are two types of the lossy compression models. Transform-based lossy compression uses the near orthogonal transform to decorrelate the data and then perform the encoding. ZIP is a typical example. Prediction-based lossy compression will predict the data point and then perform some lossy compression to significantly reduce the data size. ID3 is a typical example. And in this work, we mainly use the ID3 prediction-based lossy compression framework because it allows users to customize the compression pipeline easily based on specific demand. So we can integrate our QI preserving feature into the ID3 much more easily than based on the transform-based compression model. Okay, quantity of interest, abbreviated as the QIs, are generally used to refer to the outcome of the underlying analytics, for example, physical properties and topological features. However, preserving QIs during the lossy compression is very challenging because the impacts of the lossy compression on these QIs are unknown before post-hoc analysis. So our work will try to resolve this issue. This slide shows the framework design of our QI preserving compressor. As I mentioned previously, we are working on the prediction-based compression pipeline, which involves three important stages: prediction, quantization, and the lossy compression. And our major contribution involved a very effective QI solver, which can derive the error bound for each data point based on the user specified QI metric and also the data set. And in the following step, our compressor will perform the compression based on the derived error bound and also compress the error bound to maximize the compression ratio. And in our work, we focus on four types of the QIs, including polynomials, log mapping, weighted sum, and isosurface. And the first two types belong to the univariate category, and the last two types belong to the multivariate category. So that means we studied both of the categories in our QI preserving research. And these slides demonstrate how we developed our QI control on top of the IZ3 compression framework. Without our method, the users have to use the trial and error process to figure out what kind of global error bound should be used to preserve the quantitative interest according to the target tolerance. Specifically, the user needs to give a guess for the error bound first, and then perform the compression based on the guess error bound. And then they need to check whether the target QI can respect the target tolerance. If not, then they need to give another guess and perform the compression again, and so on and so forth. This would be very expensive. And in our solution, we have a very effective solver which can derive the error bound for each data point in the dataset according to the required tolerance on top of the QI metric. And then our compressor can just perform the compression according to the derived error bound and then get the compressed data. So obviously, our solution would be much faster than the trial and error process, and also potentially can get much higher compression ratios because of the fine-grained error bound control. Okay, and this slide shows the problem formulation about the univariate QI. A univariate QI is a function that maps a particular data value for each data point to a quantity. And a typical example is the kinetic energy. And the research target is to derive a series of error bounds for each data point in the data set according to the required tolerance on top of the specific target QIs. Okay, and in our research, we derived the error bound for many different QIs, including x square, log, or square root. And multivariate QIs has also been studied in our research. A multivariate QI is a function that maps a vector of data values to a quantity. For example, the mean value of a specific neighbors. Okay, and our research target is also trying to derive the required error bound for each data point, so that the target quantitative interest can be preserved based on the tolerance. And in our solution, we break the multivariate QI preserving problem into the multiple univariate QI preserving problem, as shown in this figure. Because of the limited time, I will skip the detail. And now let me show you the experimental results. We performed experiments on a cluster with 64 physical cores, and we performed evaluations using multiple common metrics, for example, compression speed, decompression speed, PSNR and compression ratio. And our data sets spans across different domains, including weather simulation, cosmology simulation, and quantum chemistry simulation. They are all from the real world simulations. Okay, and this slide demonstrates the compression ratios based on preserving x squared univariate. The left-hand side image showed that with the same the distortion about the preserving x square, our compressor can have the highest compression ratio. More specifically, the lower bit rate, the higher the compression ratio. So you can see that our compressors can lead to about 4 times compression ratio improvement compared with other related works. And our compressors may have longer execution time compared with the ID3 and the IP. This is because we need to calculate the appropriate error bound for each data point, which may introduce some overhead inevitably. And this slide show the comparison between our solution with another very important related work, Lee Price to OPT, and also manual tuning results. Lee Price to OPT had been published in TPDS recently, and it is a very effective search algorithm to find the best compression error bound for different compressors. But it need to run the compressors physically, so it could be very slow. Okay, as shown in this figure, we can see that our solution still get the highest compression ratios compared with the other two related works in most of the cases at the same tolerance of the quantitative interest, the Q x square. And our solution can still respect the error control for preserving the x square very well. And we also evaluate our solution using multivariate QIs. And this slide just to show an example. We can see that for the isosurface, our solution can guarantee 0 false negative, 0 false positive, and 0 false shape. However, other solutions all suffers very large distortion of the data with respect to the isosurface. We also demonstrate the visualization, which can show the effectiveness of our solution more clearly. We can see that at the same compression ratio, about 130, our solution can have identical visualization compared with the original raw dataset, but all other solutions suffered very large distortion on the visualization. Okay, and this slide shows very interesting results. We showed that our solution can allow users to combine different QIs, for example, x-square, log, and isosurface. If the users adopt, switch on all the 3 functions, then our solutions can preserve the can generate the decompressed data that preserve all of the 3 QI metrics meanwhile with a certain high compression ratios. Okay, so the user can switch on or combine their different QIs as they want. This is very important for the practical usage. Okay, now let me conclude this work. We developed a set of theories to preserve the different QIs. More details could be found in our paper, and we also implement our solution in a lossy compression framework, and our solution can get much higher compression than the related work. And in the future work, we will further improve our performance. And we acknowledge the funding support of DOE, ESCAR, and ECP, and also NSF. Thank you very much.